All right, reaction video number 10. This time I did a search for, I didn't even spell it right. Physics, spelled wrong apparently, HW, chapter 12. And we've got some electricity, magnetism, circuit stuff it looks like. So let's get started.
Questions and problems for chapter 23, except for the last section or two which deal with capacitors in series and parallel. We'll be dealing with that soon. At any rate, what we've got here are three resistors. They're in series with each other.
So this is pretty cool. It looks like what he's done is written out all of his solutions on paper. It looks like there's several pages of it, and then just screenshots that he's doing video over. And one of the really, really fascinating things that I always ask my students to do is you can see his mouse. So, at least we know what he's going to talk about. So I think that this is an awesome use of technology. It's actually pretty straightforward. Obviously, you need the screen recorder, but that's relatively straightforward. And then, decent, I don't know if these are photographs or scans. They might be photographs. If this was a scan, this would have been resting right on the bed of the scanner. I don't know if we can actually tell the difference, but really well framed. Taking a picture of your pages is hard to get it perfectly rectangular, although of course there's adjustments you can make after the fact. But anyways, it looks great, and I'm curious to see what's going on here.
And you have a graph that looks like this. And the question
Cool.
was which of the has the most current going through it, and which is the greatest resistance to lowest resistance. Well, the current has to be the same at all points because this is a series component.
Awesome.
The current coming in over here has to go through R1, R2, R3, and then out.
This is such a great question, right? I mean, the fact that my guess is this is what was given in the problem. First question, hey, who has the most current? Is such a great sort of head fake, right? Because this is, all the current has to be equal. And so you're just constantly, hey, you get that, right? Because this graph makes it seem like, oh boy, this resistor didn't do as much, and this resistor kind of gobbled up all of the voltage, the energy. So, it's kind of a head fake towards maybe this one has the highest current. But I love part A of this problem because, we have to say, well, hang on a second. There are different things going on in these resistors. Clearly, based on the slope of this graph, but there's not a current difference. Also, the x-axis of this graph is really interesting, right? It's just position, like physical position in the lab, because this is kind of a hard axis to talk about when you're talking about resistors, especially when you're not really sure what's going on inside of them. So that's pretty interesting.
So it's the same everywhere, as is true in any series circuit. For part B, if I look at this, the change in voltage has got to be larger across the resistor with greater resistance. So we know through Ohm's law that V equals I times R. If the current's the same through all these, then
Cool.
This, which is the steepest, would have the greatest resistance. This, which is the next steepest, would have the next greatest resistance, and this would have the least resistance.
Cool.
So R3 is greater than R1, is greater than R2.
All right, we'll do one more here.
9, it's asking you to figure out how the potential difference from A to B compares from the potential difference from C to D. And it told you that these were the same batteries.
Cool.
Each resistor was identical. So there's 3 resistors in this circuit, 1 resistor in this circuit. So the potential difference across A, B, and C, D has got to be the same, since those regions encompass all the places with voltage drops or resistance.
Yeah.
So
yeah, and this problem, could be made a lot more challenging if we were to talk about internal resistance. Because if you ask the question, well, which one of these is taxing the battery the most? Probably this one is. And so, in fact, you get a slightly less voltage measurement from A to B than you would from C to D. But I talk about this all the time. You build muscle slowly with you start with sort of idealized things. And so if these are perfect batteries, or they have really small internal resistance, like half an ohm, and these are all kilo ohm resistors, right? If the internal resistance in this is half an ohm, and this is a kilo ohm resistor, if you're talking 1,000 versus 3,000, two significant figures, the voltage would be the same. And so I think that it's really, really great. Kind of like the head fake on part A of the previous problem here. It's like, it doesn't matter what's happening on the right-hand side. All that matters is what's happening on the left-hand side over here, because hooked up to the same battery, boom, same voltage.
Although all that voltage will be used across this one resistor, and that voltage would be lost across 3 of these resistors, the particulars of that are that all this.
So a couple of hitches, a couple of pauses in his voice, and you know that I love this, right? I love trying to watch a teacher really think critically on the fly. And I'm going to make some guesses here. I am going to guess that as he was looking at what I'm guessing is his own writing, he saw I2 and I3 here and realized that he didn't write a separate, I don't know, I4 here or something. You could just sort of run through it really quickly and say, oh, all of these currents are the same. You can look ahead and see that he's done that. But the fact that there's 3 resistors here, it's kind of weird that he only labeled 2. So I'm curious if that was what the hitch was. And of course, looking sort of ahead at what he's got, I actually don't think he needs to correct that, but I'm just curious to see if he does.
Voltage drop is between C and D, and all this is between A and B. And that would equal the potential difference across the battery. So when I look at this, it's asking to rank the currents. So since there's one resistor here and the same voltage across this.
Oh, so it wasn't him. It was the problem. The problem decided to do it this way. So it's possible his hitch had nothing to do with that. But if that's true, this is a really interesting problem. Like it's having you ignore that middle resistor. And ignore the current through it. But it's literally not asking about it. It's like, hey, rank these 3 currents, which is sort of interesting, right? Because if you were to put this one in there as well, that might quickly drive home, oh, well, of course all 3 of these are the same. So by skipping one, it's making the student think, oh, there's something interesting I should be able to do here. So that's really interesting.
This battery is this battery. We would have I is equal to delta V divided by R. This has lower total resistance, so this has greater current. I2 and I3 have got to be the same because this is a series circuit. So current everywhere in a series circuit is the same, although current in different series circuits, with different batteries and different resistances, could differ. But in this plate circuit, there's only one path, so these 2 have got to be the same current.
Cool. We'll keep going. Why not? These are going past. I just realized what this is. Oh my gosh. So this notebook here, I'm blanking on the company, but I used to use these, right? So these are actually really, really, really cool. So basically what happens is on the background of the paper is these tiny little dot patterns, and the pen that you use has a tiny little camera looking at those dots, and it can tell where it's at on the page. And even cooler is built into the pen is a microphone, so that it can actually capture your voice where you're drawing. And so you can actually, as you're drawing, you say, well, let's draw a graph here. And when you play it back, you can do it on their website or you can do it on your own computer, literally the stroke is filled in while you talk. And what I used to do is I had like 10 of these, and I would loan them out to my students and say, okay, who wants to do one of these homework problems tonight? And I would pass it out to my students and say, okay, here you go. Just give me the notebook and the pen back when you're done. And then I could assess them by looking at their work and listening to them. I'll tell you what, though, this technology was fantastic and worked really, really well. The problem is the company decided to take out their processors because they realized that everyone had a super awesome processor in their pocket, their cell phone. So this company, as far as I know, shifted over, I think it's called LiveScribe, by the way, LiveScribe. They shifted over to the pen doing very little of the work and actually having your cell phone doing most of the work. And I was just so frustrated because they actually shifted over their website. Their pens, literally, you couldn't upload it to their website anymore. So I still have 10 of these pens lying around with very little I can do with them. I thought it was a fantastic technology. I'm curious, he could have done these videos by simply giving these links to his students so that they could actually watch the strokes be filled in while he was talking. But it's fascinating because what I've noticed, what my students have noticed, is that they would rather write it all first and then talk later so often. So if a student does that with a book, what they could do is write it all first, then hit the record button. So you just literally press right here. I know, isn't that cool? You press the record button with your pen, And then what you can do is you just have to make tiny little tick marks. So you make a little tiny tick mark here to get the pen to realize that's what you were talking about. And then you can sort of lay out what you're up to. So sorry for that tangent there, but I'm really excited about this technology. How old is this video? This video is not old at all. So maybe the company is back doing it like this again. I'll have to check. Very excited.
Oh, that's my finger. That's weird.
Little humanity there.
Problem 9, got 6 volts, 2 ohms, 1 ohm. It says, it gave you this graph, and it asks you to actually show what the circuit looked like. So if it's 6 volts and 2 amps, that means the total resistance is 3 ohms. And I know that I'm going from 0 to 6 volts at some point, so the battery would be 6 volts. So if I start here, I would drop these 2 volts. Well, if I have 6 volts and 2 amps, again with 3 ohms, that means this would be the 1 ohm resistor, the one I would encounter.
This is a really, really great multi-representation problem. So it sounds like what was given is this drawing and this information. And you're basically supposed to figure out what the resistances are and say, okay, well, I dropped 2 volts. Oh, this is very cool. I love how he set this up. I love how he's talking about it.
Counter first. I'm only dropping 2 of the 6 volts here. At 0 volts, and then I cross this, I'm going up all 6 volts. The wire is where the voltage is flat, and then I lose 4 volts here. 2 amps times 2 ohms means I'm going to have a potential difference of 4 volts, and I go from positive 6 to positive 2. And that's where I end up, which is the same location where I started.
Awesome. So I'll stop right there. So lots of really cool things going on here. I think, first of all, these are really interesting problems. They get the students thinking. They show some head fakes towards doing it differently. Sort of wondering about, oh, does this matter? And I think he's doing a really great job of walking through, just the fundamentals. Like, look, well, these currents have to be the same, or here we have this drop. I think that the way he did this problem was really great. He encouraged people to start here and go clockwise. I'm not sure if that was in the book or not, but he immediately said, okay, well, if it's 6 volts and 2 amps, we know what the total resistance has to be. He knew that the total resistance had to add up to 3, but there's lots of ways you can add up to 3, right? Interestingly, yeah, so that's a good double check. I was just trying to think, could you interpret this in any other way? Certainly you could go along here and say, oh, well, there was a drop. Well, it was 2 amps, 2 ohms. This has to be 1 ohm. And you could come up here and say, okay, here's another drop. This is 4 volts. Well, if it's 2 amps, this has to be 2 ohms. And then he could have said, oh, look, sure enough, it adds up to 3, which is exactly what this has. So I think that he did it in a slightly different order, but he nailed all of these ways of double checking yourself when doing these problems. Very, very cool. Well, thanks everybody. This is number 10, which is kind of exciting. I'm really enjoying these. It's a great way to start my morning. Remember, physics teachers are awesome.